Yeah, I see it. Yeah.
Okay, good. Then I'm going to share, as you said, the contribution from Francesco. So I will start right now.
Also, I don't hear any audio. Are we supposed to hear something or?
In principle, I'm sharing also the audio, but apparently you don't. It's not forwarded.
So is it only me? I don't know. Did anybody hear the audio?
I also don't hear, Paul, the audio. I hear the voice, but not the audio.
Okay, what about now? Just let me try again.
Nothing.
No. Assuming that Francesco is talking.
Okay, no, then okay, let's see. Because I hear the audio here, so you don't even see it from the microphone. Okay, so let me try again. Let me try to share it again. Can you hear it now?
No.
Oh, no.
Okay.
Let me try to.
Did you? Sorry, if I interrupt you. Did you try to enable the audio from the PC when you share the file? You have an option. Just if you have to stop the sharing and restart. But when you press the share button,
okay,
on top of your menu, it appears a note about.
Great, I see it now.
Include computer sound.
Include system audio. Yes, that was very nice tip. Thank you.
Oh, you're welcome.
Okay, then I started from beginning. Okay.
I want to present the work that we did inside the ALOHA project on hardware quantization and pruning with NEMO. Bringing deep neural network inference to the extreme edge is considered very attractive. This is because executing directly on a device sidesteps any problem in transmitting raw data from a device at the edge to the cloud, which of course could be hit by problems in privacy, security, and also by the raw cost of transmitting data via the radio. On the other hand, it is clear that executing directly on device is potentially very expensive, especially because deep neural networks have typically a large memory footprint. Take, for example, MobileNet and other networks that are typically considered as in the state of the art for what concerns the ImageNet benchmark for deep neural networks. If you look here, you can see clearly a Pareto frontier, which shows that smaller networks, such as MobileNet, which I cited, are much less accurate than larger networks. And most of the networks that are on the Pareto frontier with acceptable accuracy are actually larger than the level of memory, than the amount of memory that we can have on an ultra low power on-chip memory, which is around 1 megabyte. Most actually are beyond 10 megabytes. This means that in order to actually implement the networks of this complexity on a real device, on a real ultra-low power device at the extreme edge, we need to reduce their memory footprint. One of the most important techniques to reduce a deep neural network's memory footprint is, of course, quantization, which is replacing floating point operation with integer or fixed point ones. This is also a significant impact on the complexity of the operations themselves and helps reducing the memory, not only the memory, but also the energy footprint of such operations. This relies on the fact that deep neural networks are composed of layers of linear and nonlinear transformations applied one after the other. The linear part of the transformation is typically can be realized with integer valued data, which is then squashed into a smaller space by the activation function. If we properly constrain the activation and the weights of the linear transformations, then we can quantize the network, in theory, arbitrarily to a lower number of bits. Another fundamental technique to reduce the size of deep neural networks in memory is pruning. In particular, the most common way to do pruning is magnitude-based pruning. The idea is to eliminate weights which have a value lower than a certain threshold, and if necessary, perform some retraining steps using masking in order that the accuracy of the network is then conserved. In the context of the ALOHA project, we developed NEMO, or Neural Minimization for PyTorch. If we look at the full stack of tools necessary to deploy deep neural networks on top of optimized hardware and architecture, our tool only occupies a small part of it, but it is a crucial part. It takes over a part of the training procedure. It leverages several techniques for quantization and pruning, and it also performs part of the graph optimization that is then necessary to deploy things and deep neural networks in hardware. The key idea of NEMO is to treat deep neural network quantization as a lowering procedure, much like a compiler's intermediate representations. In particular, NEMO uses 4 intermediate representations. The first one, full precision, is just plain PyTorch. The second one, fake quantized, is where we introduce quantization-aware primitives in order to make the network representative of quantization, but still fine-tunable by a training procedure. Quantized deployable removes some of these in order to make the network more representative of real quantization necessities. Finally, integer deployable is fully representative of an execution only using integers for all parts of the network in hardware. And so it makes integer-only hardware results fully reproducible in Python. NEMO is implemented as an imperative library which extends PyTorch itself and can be integrated easily in existing PyTorch scripts and flows. NEMO's fake quantizer representation relies on a simple idea, that is mapping tensors that are real valued to integer numbers. Here we have an example with a quite a common convolutional layer followed by a ReLU activation. We have 4 tensors overall, W, X, Phi, and Y. W is weights, X is inputs, Phi is the intermediate results, and Y is the final outputs. Here we want to represent all of these with integers using linear quantization, and we will rely on a method which is called PAKE. The real valued weight tensor is represented naturally between 2 bounds, alpha, the minimum, and beta, the maximum. In order to quantize it linearly, what we do is essentially introducing a set of steps between alpha and beta. In particular, in linear quantization, these steps will be all of equal length or width, and they will be of size total epsilon, like here, which is given by beta minus alpha divided by the number of steps minus 1. If we want to represent the steps with q bits, it will be 2 to the q. The number of steps will be 2 to the q. How do we do this? We essentially introduce this step function, which we call big Q of W, on top of the weights. For activations, we do not always have an explicit clipping range. For example, ReLUs only clip at the minimum 0, but have no bound for the maximum. In order to introduce one, which is necessary to introduce the stepping function like we did for weights, we extract it statistically by looking at the frequency of values over a certain calibration set or the training set of the network itself. This makes it possible to extract a range alpha, which we then introduce as explicit clipping, even if the range is not statically fixed at the beginning. This allows us to introduce also here a stepping function working exactly like we did for weights. This is then directly integrated into the activation function because the activation function is itself nonlinear, much like the stepping function itself, creating essentially a Q-ReLU. In this way, we represent X, W, and Y as integer numbers. But what do we do for intermediate numbers such as 5? The problem is more general. In fact, the fake quantized strategy that we use till now that allows a network to remain fine-tunable does not explicitly represent in an accurate way the precision at all stages. Not only the intermediate representation is a bit fuzzy in terms of numerical precision, but even more, batch norm, average pooling, max pooling operations are all used in real value in order to be fine-tunable, and therefore cannot really be treated as fully quantized and do not represent an accurate model of what will happen on hardware. There are essentially two solutions. One is to use static fixed point to represent real values, but this means that we have to choose a set of clipping parameters that are power of 2, and it's very rigid and does not scale well below 8 bits. The solution we follow in NEMO is the second one that we propose here, that is to accurately propagate precisions through all of the nodes of the network, which are then represented with quantized models using dynamic fixed point. This requires all models to have a minimum representable quantum, much like we introduced for weights and activations. But it can still be brought to a full integer representation, quantizing all parameters, including batch normalization, and using approximation with user-settable precision wherever required. This strategy leads to transformations such as the one that is shown here. That is, representing the network fully with integer values, integer parameters, and integer tensors flowing through. This kind of network can then be exported in an NX format and brought to the next layer of the tool flow, without loss of accuracy or with controllable loss of accuracy. In ALOHA, NEMO is the main mechanism behind the refinement for parsimonious inference engine, or RPI engine. That is, the tool that allows to take a network and reduce its precision of representation without losing accuracy, or losing accuracy in a controllable way. It does so by using extensively quantization and also applying a form of unstructured pruning, magnitude-based pruning. First of all, RPI uses NEMO to transform a network represented using normal PyTorch operators into a quantizable network. Then, in ALOHA, we use a relaxation strategy, novel contribution with respect to the state of art, which iteratively fine-tunes the topology to lower and lower precisions by taking a certain network, fine-tuning it to let's say, relax the precision, evaluating the convergence rate, and then lowering the precision in a progressive fashion. The output of this procedure can then be exported in an NX format using NEMO again for exchange with other submodules. For example, starting from a pre-trained floating point MobileNet V1 with top 1 precision of 69% on ImageNet, we can observe the working of the relaxation procedure. First of all, it will evaluate the precision by taking the network and quantizing it without any fine-tuning. We see that, for example, in this example, the precision collapses for everything apart from the 10 by 8-bit configurations and the 12 by 8-bit configurations. The lowest one, for which the precision has not totally collapsed, will be the objective of the following relaxation procedure. So this network will be taken, transformed with NEMO, and then fine-tuned using the fake quantized strategy. After fine-tuning with 10 weight bits and 8 activation bits, the network reconverges to the original top 1 accuracy. The procedure is then repeated, evaluating again what happens if we reduce further the precision of the weights and activations. And in this case, the network collapses in many cases, but it still retains a good representation power down to 8-bit weights and 6-bit activations. So that will be the next step of the relaxation procedure. So now we train the network further at 8-bit weights and 6-bit activations. And what happens is we get again to the maximum precision that we had at the beginning with some noise, so 69.3%. We can continue this procedure further and further and further, and we obtain a progressive small reduction of precision at the beginning, and after a while, a more significant drop. And again, if we reduce more and more, we will see a more substantial drop after a while. Still, we are able to obtain a network which at 6-bit weights and 4-bit activations achieves 65.5%, so only 4% drop with respect to full precision accuracy. Using NEMO's integerization procedure, this precision can be kept even when moving to a fully integer representation, accurately representing hardware. If you consider memory footprint, the original footprint was 16.4 megabytes using floating point, which is directly reduced using lossless compression to 3.33 megabyte of footprint using quantization. These can be still further refined using unstructured pruning of results that are within 10% of the average channel value, yielding the same 65.5% of top 1 accuracy. Overall, the footprint of the network can be contained within 1 megabyte, enough to fit on an ultra-low power device entirely on chip. NEMO is open source using a liberal Apache 2 license and is available on github.com/palplatform/NEMO. You can also find additional material online at the links pointed out here. I thank you very much for your attention and hope you enjoyed the presentation. Goodbye.
Okay, yeah, I think this concludes this talk. Yeah, so if you have questions.
Anybody has questions? Okay, that's not seem the case. Thank you, Alfio. So we can move to the next talk. I think it's gonna be given by Elias, right? I don't hear you.
Yes, Paolo.
Yeah. Okay. Now I'm hearing you. Okay. So the title of the talk is Runtime Pruning of Deep Convolutional Neural Networks, yeah. So stage is yours.
Thank you. Hello, everyone. This is Elias Theodakopoulos, and then I'll present you the contribution of Eva Labs to the ALOHA project, which is a component that enables a trained model, the conversion of a trained model to a model that has capabilities of runtime pruning of convolutional kernels. Just for a brief introduction regarding the rationale and the motive of our contribution. In classic pruning strategies, the algorithms usually aiming at zeroing as many coefficients of the models as possible with the objective of obtaining either a more a shrinked model for either saving memory or computations or both. And in there are, of course, several variations of such algorithms. In the unstructured version of these algorithms, the obtained models usually have a sparse structure, which means that they require usually specialized libraries that can handle sparse multiplication efficiently in order to interpret such gains to inference time benefits. But of course, there are also structured variations of pruning algorithms which can prune off whole kernels or larger structures of such models in order to enable more conventional, let's say, inference frameworks to benefit from these operations. Either way, these algorithms produce models that have a static structure which is smaller than the original one, and of course they can offer high throughput through the same inference engines because they have no branching, additional branching inside them. But essentially, the inference effort is the same regardless of the data instances that process each time. Our goal in this project and in this component especially is to create a mechanism that can create a model that can adjust the inference effort on the specific process datums, which means that it can infer faster for easy, let's say, samples. Easy, of course, is something relative to the task at hand, or it can activate more resources and have a slower and more thorough inference for more difficult samples. In the context of convolutional neural networks, the most straightforward approach to obtain such behavior is to enable the model to decide whether to skip the computation of some kernels or even whole convolutional layers if the architecture of the model enables that, such as residual networks and stuff like that. So our aim into that is to create an algorithm that can create models that those skip decisions are produced by the model itself in specialized components inside the model, specialized nodes, where the skip decision, the decision rules themselves, skip decision or gating signals, or these are equivalent, let's say, terms. These rules, we need them to be learned simultaneously to the regular training of the model, or through conventional backpropagation training algorithms, so as to be compatible with any training engine. Of course, such a mechanism creates a model that has branches into it has conditional execution of kernels, computation of kernels, so it has branches in the inference graph. So it is a challenge to convert the theoretical gains, computational gains, into actual inference time gains on the target hardware. Our component inside the whole ALOHA tool is depicted here. Our tool is rather a satellite tool where it belongs to the work package 3 tools, and it aims to get an ONNX description of an already trained model, an optimized model using the previously presented tools of the ALOHA toolchain. And of course, the data set at hand, some error margins defined by the user, and a decision whether the produced model has can support dynamic execution or not, and produce a new model, a new optimized model which is either statically or dynamically pruned. Some details regarding the underlying mechanism. The overall, the most straightforward, let's say, overview of an algorithm that can achieve all these objectives that I described earlier is a scheme like that, where for each convolutional layer which we want to transform to the dynamic one, we need to train a set of a new component. We insert a new component in the computational graph, which is of course a learnable component, and it operates on the data that the convolutional layer gets into its inputs, and create gating signals for each one of the underlying kernels of the convolutional layer. The most straightforward, the most simple, let's say, approach on that is to have a scheme like that, where we can learn simple linear rules on the channel-wise pooled data of each layer's input. And in order, of course, for that to be able to be trained on a regular backprop manner, this whole operation needs to be differentiable. So the simplest way to achieve that is to use a sigmoid function in order to have a soft transition between inactive and active kernel during training. So gradually during training to weaken the unnecessary, let's say, kernels in each instance, and train the model to predict values towards 1 for very significant kernels for each datum. So essentially, for each graph that we want to modify to dynamic one, we perform that type of modification in the overall computational graph, with the addition, of course, of a necessary loss component, which is added to the overall loss function of the optimization problem, which is a component that is essentially the L1 norm of the switching of the gating signals, which incentivize, of course, the whole optimization process to use less and less kernels as the training proceeds. So even this whole implementation is very simple. We wanted to evaluate whether this thing works, whether this all this mechanism adapts as we want and has the characteristics that we want to achieve. And to that matter, we present the results on a small ablation study, let's say, using two convolutional neural networks, CAFNet and SqueezeNet. CAFNet is similar to AlexNet, and SqueezeNet, which the two layers are the two CNNs have significantly different sizes in terms of computational effort. CAFNet requires about 700 million multiply accumulating operations. SqueezeNet is roughly the half of that. So we also evaluate this procedure on two main and one extra tasks of varying difficulty, starting with, of course, the standard image benchmark with the 1000 visual classification categories, and moving to Food 101, which is a visual classification task with 100 categories, and of course a much easier task of distinguishing between pictures acquired in day and night in the Flickr dataset. And as we can see here, the the computational gains achieved by the converted models, it's smaller, of course, for the more difficult task. Of course, compared to the reference, its respective reference static model, are smaller for the more difficult tasks. Moving on to the full data set, we can see that, especially for the CAFNet network, the extra redundancy of the network is removed from the network, achieving 85% reduction in the computational load. Of course, this is average because it's dynamic and each datum has its own computational load, but this is an average reduction overall the evaluation set. This change is much smaller for the smaller SqueezeNet, meaning that, of course, it is a small model, so it is less redundant to the model to remove. And we can see that moving from a more difficult to an easier task, of course, for the same model, the overall reduction in the computational load is higher and higher, which means that the whole procedure adapts as we want it to behave. So the big question is, can these theoretical gains, computational gains, be translated to inference timing gains? To see the challenges on that, we have to see what this method produces. A trained model, its training model by this process has, of course, a set of kernels which are permanently pruned, which this graph shows that a lot of kernels are of the transformed model are always off, which means that they can be permanently pruned from the model. But there are also some kernels which are always active, which means that it can be handled as regular static kernels with no branching operation. But there is also a significant part of kernels which are conditionally executed or conditionally computed based on each specific datum. Of course, by this procedure, we can also produce a completely statically pruned model by deciding a threshold to the utilization and with chopping off all kernels that we believe that are not significantly enough, and with a slight fine-tuning, you can produce a statically pruned model too. But of course, for the dynamic one, which is the main objective of this tool, the significant challenge is to assess how these can be translated to an inference time gain, especially for heterogeneous hardware architecture with GPUs and CPUs such as the mobile system on chips and hardware like that. So we tested that using an architecture, a software architecture like the one on the left, where on the CPU, the code on CPU decides essentially executes the branches which decide on the create the gating signal or the skipping signal, let's say, which means that CPU decides which kernels need to be executed on its computational node, dynamic computational node of the network. Then, based on those decisions, CPU reorganizes the coefficients memory in order to remove coefficients that correspond to kernels which are not going to be computed, and then initiates the GPU computational course, which then the actual execution of the kernels is taking part to the GPU, and the results are going back to the CPU, where gathers data and reiterates for the next node of the computational graph. Using an architecture like that can give significant inference boost in significant boost in the inference time and the throughput of these algorithms. We can see here for both for SqueezeNet and CAFFNet on the previously shown models, it can achieve, this architecture can achieve up to 2 times speed up for the SqueezeNet architecture into the Snapdragon 820 SoC. If someone wants to see some details regarding the memory organization and of GPU and the implementational details, you can refer to this publication. And of course, this thing works. We've seen that the results can be translated to inference time gains, but there are the formulation that I showed earlier has some disadvantages, let's say, because of its simplicity. The L1 regularization term is not strong enough regarding the sparsity, the enforcement of sparsity into the gating signals. So the dynamic or the enforcement of dynamic behavior. So there are many tasks where the trained models either converts it to a completely static mode, or the gating signals stuck into some intermediate values which cannot be threshold in inference. The first one, it's not so bad, but still it is a pruned model, but lacks the dynamic, the benefits of dynamic behavior. The later one is a little problematic for inference. And to overcome this problem, we evolved the algorithm by changing the formulation of the learning problem, essentially moving from deterministic gate signals to incorporating stochastic gates, where the underlying distribution of the stochastic gates is the hard concrete distribution, which is shown here, which is essentially a stretched sigmoid clipped into 0 and 1. Why using such distribution? The reason is that by using that distribution, we can include a more sparsity-oriented regularization term into the overall optimization problem. By using that formulation, by introducing terms like that for each convolutional layer to the overall optimization algorithm. If someone wants to see details why this formulation leads to that kind of zero norm regularization, you can refer to the publication shown here. By using that formulation, essentially the LCAMs predict not directly during training, the LCAMs predict not directly the gating signal, but essentially the log A parameter of the hard concrete distribution, which means that the LCAMs are, the higher the log A signal is, the more probably it is this kernel to be active during the forward inference during the training phase. So essentially, the gate signal has a sense of how each underlying kernel, how much it's valuable to the overall inference. Of course, during inference, the log we use the log A parameter, log A signal is essentially the decision of whether this kernel needs to be executed or not. Some other algorithmic aspects that we evolved is the automatic selection of the best layers to convert to dynamic, where the most gains are predicted to be found. And of course, the rapid automatic exploration of several configurations of the regularization strength along the different kernels of CNN architecture. And of course, in the end of this procedure, to select the best solution for the constraints set by the user. Some results regarding some results on the use cases in the context of the ALOHA project can be shown here. We can see that, for example, for the keyword spotting, it's a classification task with a reference model with 94% accuracy. There are several solutions that can be selected for various types of constraints. If someone needs essentially no loss on accuracy, can select the model shown at the right-hand cycles. We can see that with essentially zero loss on accuracy, we can achieve up to 75% of average reduction in required operations. Of course, if someone can afford the margin, a loss in accuracy, has a margin loss for accuracy, these gains can be even further, up to 45, to get a model which needs only 40% of the initial computations. Similar results for the medical use case scenario, and as also for the detection, pedestrian car detection task using the YOLO architecture, which with a marginal loss in accuracy, we can get a model with that requires only 52% of the operation of the reference model. In conclusion, with all this process, we've seen that actually a runtime pruning of kernels is indeed efficient for heterogeneous architecture. That models can achieve parsimonious inference. This behavior that exhibits parsimonious inference for easier data and more thorough inference for the more difficult ones, and such training procedures can adapt to the model, the model's intrinsic redundancy, to the task's difficulty. And of course, all these theoretical gains can be translated into inference time gains in modern SoCs, despite the branching-induced delays. A clever software architecture can translate those flop reduction gains to actual inference time gains. That's all from me. Thank you.
Thank you, Elias. Are there any questions? Very fast, because we have been running a bit late. Doesn't seem that we are having any question on this. So next talk is Battista Biggio from ProResBoost 1. And the title of the talk is AI Security at the Edge. So Battista, please.
Yes, I share it. It's installing a driver now.
Windows.
Okay, should be able to do it. All right, I guess you see the screen.
Yeah, I see it.
Okay, thank you. I think I can just briefly recap what we as ProResBoost 1 did in this project. But let me start by, reporting some basic facts on AI. We all know, and I think we agree that this technology, mostly machine learning and deep learning, has achieved unprecedented success in many applications, ranging from cybersecurity, robotics, and others. And it has been defined even the new electricity from Andrew Ng, who is a prominent AI scientist professor at Stanford. There are many examples of successful applications. As I said, here you see, for instance, the current state of the art in object recognition. From I think this is from Facebook AI research. It's the former version of one network for object detection. There is other very popular examples on speech recognition. So I guess all of us know that you can talk with your preferred device on mobile phones and tablets and so on. But I mean, is this AI or this technology really smart, and can we trust these algorithms, or there are issues? So to make a long story short, the answer is no. And there have been countless papers now showing that you can actually trick these systems by applying very small perturbations. So here it's one of these examples where you have an image of a school bus, which is correctly classified by one of the ImageNet state-of-the-art models. But if you basically compute a small perturbation that you can apply to the image, then you mostly get the same image as before, but this time this is misclassified as an ostrich. And now the way this noise is computed is not random. So this is not random noise, but it's actually noise which is optimized against the learning algorithm in a way that you can apply this bounded perturbation, small perturbation, and let the source image cross the boundary to be misclassified as something different. So that's what is conceptually represented here. And there are also more sophisticated examples, so like attacks that have been demonstrated in the physical domain, so in real world applications. Here you see that you can apply these stickers on traffic signs to have them misclassified. And you see that the car consistently misclassified the speed limit, the stop sign on the left as a speed limit due to the presence of these stickers. There are examples also on attacking audio to text transcription classifiers. So here I have, I will just play an audio and you will see how it is transcribed by Mozilla Deep Speech. So the first one is the original audio. I hope you heard that, and the transcription is this.
We didn't hear. I don't know if you have enabled the.
Yeah, I did it, but it says that probably I had to reboot Teams. So never mind. I mean, it's
okay.
Just the exact.
Okay, we trust you. We trust you.
Yeah. I will share the presentation afterward. But then and the next audio is just the same sentence, which is only slightly manipulated to. I mean, humans can still perceive the same sentence, but this time it's transcribed as something completely different. So here you see that the result is, okay, Google, browse to evil.com, which may send Alexa to surf on some malicious website, for example. So now going to the AI security aspects in this project in ALOHA, we were in charge of developing this security evaluation tool, which is part of the characteristics of the features optimized by the design space exploration engine. And this tool works as follows. So the goal here is to provide an assessment of the robustness of machine learning models against this kind of adversarial perturbations that I described before. So as input, you take the tool takes the ONNX model of the network under analysis, the data which is used for testing, and the kind of perturbation that is applied, because you can select different types of noise based on, for instance, different notions of distances, or even apply random noise. And the output of this evaluation will basically show how the accuracy of the model decreases as the perturbation level is increased. So as you increase more and more the size of the perturbation that is applied on the images. And the idea is that the more gracefully these curves decreases, then the more the classifier or the neural network can be retained robust. So it's less sensitive to input changes. And to characterize this behavior, we then compute let's say a qualitative level of security, as you see here, low, medium, or high, depending on how much this curve decreases, on how fast it decreases. The tool is open source along with the other ALOHA tools in the repository that you see there. And we also have supported the implementation of a mitigation technique, so to improve robustness of neural nets, which works in some use cases, and it's basically based on the intuition that to improve robustness of neural nets, one of the most successful techniques aims to retrain the model using the perturbed examples with the correct label. Now, this essentially amounts to solving this complex optimization problem, where you minimize the classic loss that you have for training, but it is optimized on samples which are perturbed in a way that instead aims to maximize the same loss. Now, so this is a min-max robust optimization problem. The nice thing is that in some cases, by linearizing the function, you can solve the inner maximization problem in closed form. And what you see here is the solution. And so basically, this allows to greatly reduce the complexity of the approach, because you are not anymore required to generate these perturbed samples and retrain on top of that, but you can just modify the loss that you optimize during training by essentially crafting the regularization term depending on the kind of noise that you assume here. So this depends on the kind of perturbation that you model here. Okay, so that's and basically the effect that you observe on the classifier is that the decision function of the model becomes smoother. So what happens is that you're pushing the decision boundary farther away from the training points, and this gives you sort of more robustness against these small perturbations. So coming to some use cases in ALOHA, we tested this approach both to evaluating security and improving it on the keyword spotting use case. So here the goal is to take input speech signals and classify them. So these are short keywords, and these signals are mapped onto a frequency time representation, and then they are fed into this neural net that outputs the decision on 10 classes. We did the analysis here by perturbing the spectrum, here the frequency spectrum of these signals, which again can be inverted to generate the corresponding audios. But as you see, basically the vanilla model, so the undefended one, is the red line, is very vulnerable to even very small perturbation of the spectrum. And if you plug in this regularization term, you can increase robustness by a tiny bit in this case. But what's more interesting here is probably that you get something which is more robust under random noise even. So it seems that improving robustness against the worst case also gives you more robustness in let's say, less adversarial cases or random perturbations. And here again, I have some examples, but I think given that you cannot hear anything, I will skip this. And then we did the other application that we investigated was the object detection and recognition with YOLO. This is fundamentally different from the classification task, because here you're given an image and you want to predict objects, the kind of object and its position in the image, and you can also have multiple objects, as you see here. So the idea used by YOLO is to make to predict a number of objects in each box, and each object is predicted as by computing the probability that an object is actually there, as you see here, and predicting the corresponding bounding box. And then for each object, it is also the classifier tries also to predict which class this belongs to. Then the idea is to predict, let's say, a larger number of objects and boxes, and then pruning the boxes afterwards to refine the predictions. Now, the idea that we followed for attacking this model and evaluating its robustness was actually to perturb the input pixels in a way that the probability of the object here predicted for each box can be actually lower or higher. And the effect that you get is that you can essentially enforce the network to predict more objects where instead there's nothing, as you see here in the picture. Or conversely, you can also make detections disappear. So you can have also this person being no longer detected after the attack. And then again, if you test this on the actual model, the mean average precision of roughly 0.6, which is, I think, the state of the art for this model, decreases quite quickly when you have these optimized adversarial perturbations against it. Whereas for random perturbation, it seems to stay quite stable. And here you have two examples. On the top, it's tested against a random perturbation, and below against an adversarial noise. And you see that the predictions are completely misled in this case. So you are predicting a person here where there is a group of people actually, and you're missing the foreground person here. Okay, so to conclude, we have released this evaluation tool as a Docker container. It's built on top of the open source SecML project, which we are actively maintaining, and it counts more or less 1,000 of installations, and we have plans to push this. There is a demo which is available on the company website and also on the project website. And we have been using this tool to also, we have exploited it to also evaluate some of the tools that we have, some of the products that we are building. One is the web application security product, and the other one is essentially an anti-malware solution for Android, which we are releasing on the market before the end of this year. And it's going to be evaluated with this tool and include secure learning algorithms to, prevent evasive malware variants being successful. For future plans, we have the idea of extending SecML to include other domains. So to extend the approach to other domains, you actually need to implement the perturbation models, which are meaningful for these domains. For instance, how to manipulate executable programs is completely different. It's a completely different way with respect to what you do on images. And then the final project would be to integrate these security testing tools along with a pipeline to deploy continuously machine learning models to what is called now ML operations. So that's basically what I have to say. But I don't know if there will be questions, but I'm curious to hear.
Thank you, Battista. Any question, guys? Any question from the audience? Okay, this doesn't seem the case again. So I think that in this case, I just have to welcome everybody again for thank everybody again for participating to this final workshop. I also will take chance for noticing, highlighting that today is the official last day of the ALOHA project, and well, of course we will have to meet again, but I think that it's official that it will be a remote occasion for us to meet during the review, the final review that we will have with the commission. But besides that, I think that today is our official last day inside ALOHA. And well, thanks everybody for the work that you have done. It has been a pleasure to work with you. I'm really disappointed that we couldn't share more moments together due to this pandemic that has been preventing us from traveling and from meeting in person. This has been a real pity, because the few times that we were able to meet in person, this was a wonderful group of people. So yeah, let's hope to work together again in the future. So this was from my side, and so if this is it, I think that we can close the workshop now. Okay, doesn't seem that there are other comments. So thank you everybody, and talk to you soon.
Thank you, Paolo.
Bye bye.
Everybody.
Thank you, guys. Bye.
Bye.
Thank
Bye.
you.
Thank you, Paolo.
Thank you.
Bye.
Goodbye, everyone.